Ever wondered why airliners cruise at 35,000 feet? It is a calculated balance of physics.
Climbing higher thins the air, reducing friction and allowing the aircraft to slide through the sky efficiently.
However, jet engines require oxygen, too high. And the thin air starves the combustion process of power. Lift also changes. Thin air requires higher speeds to keep the heavy fuselage suspended in the atmosphere.
This creates the Coffin Corner, a narrow corridor between stalling too slow and breaking the sound barrier.
Pilots also seek jet streams, high-speed rivers of air that provide a massive boost to ground speed.
Most storms reside in the lower troposphere, so climbing high ensures a smoother ride above the clouds.
Altitude provides a safety net. If engines fail, height translates into miles of precious gliding distance.
Finally, the fuselage must withstand intense pressure differences, limiting how high commercial jets can safely travel.
The Concorde was an outlier, cruising at 60,000 feet to minimize drag while traveling at Mach 2. This required specialized engines and immense fuel consumption, making it a masterpiece of speed, but not efficiency.
Future hypersonic aircraft aim for 100,000 feet, where the air is thin enough for extreme velocity.
For now, mass aviation chooses the middle ground, balancing the cost of fuel with the laws of physics.
Then, every flight is a continuous negotiation between the machine's power and the atmosphere's invisible constraints. The beauty of aviation lies in this precision, finding the exact point where humanity and nature coexist.
Ever wondered how a 500-ton machine stays in the air? That is a story for the next journey. To understand flight, we must look at the wing. Its specialized curved shape is called an airfoil. Air moves faster over the curved top, causing pressure to drop and pulling the wing upward.
Near the ground, air is dense, creating immense drag that forces engines to consume excessive fuel. Simultaneously, air striking the bottom is deflected downward, pushing the massive aircraft toward the sky. Simultaneously, air striking the bottom is deflected downward, pushing the massive aircraft toward the sky.
This is the marriage of Bernoulli's principle and Newton's third law, a dual force keeping tons aloft.
But wings need velocity. Massive jet engines provide the thrust required to overcome immense aerodynamic drag. At takeoff, pilots increase the angle of attack, tilting the nose to maximize air deflection.
Watch the flaps extend. They increase surface area, generating massive lift even at lower speeds. Once at cruise, these forces reach a perfect equilibrium. Lift equals weight, and thrust equals drag. To steer through the sky, pilots manipulate three invisible axes: pitch, roll, and yaw. Rolling is controlled by ailerons on the wings, tilting the aircraft to bank into a turn. Pitching moves the nose up or down, using elevators on the tail to change altitude.
Yawing controls the left to right direction, managed by the rudder on the vertical stabilizer.
Modern airliners use fly-by-wire systems, where computers translate pilot stick movements into precise surface adjustments. These inputs are coordinated. A turn requires a blend of roll and rudder to remain smooth. The cockpit is the brain, where thousands of sensors ensure the machine obeys the pilot's intent. Navigation is no longer just visual. GPS and inertial systems guide the plane across trackless oceans. High-bypass turbofans are the marvels of modern engineering, turning fuel into massive, sustained forward momentum. Most air never enters the engine core. Instead, it is accelerated around it, creating quiet, efficient thrust.
Inside the core, titanium blades compress air to 30 times its original pressure, preparing it for ignition.
And in the combustion chamber, fuel mist ignites, creating a turbines.
These turbines spin the massive front fan, creating a self-sustaining cycle of power and air intake. Modern engines are designed for ETOPS, allowing twin-engine jets to fly safely across the world's widest oceans. Even if an engine fails, the remaining power is enough to keep the aircraft climbing and flying.
This redundancy is the cornerstone of aviation safety, ensuring that every journey reaches its destination.
Beyond physics, safety is maintained by invisible electronic shields guarding the aircraft's perimeter and flight path. Weather radar scans the horizon, detecting moisture and turbulence long before the pilots can see it visually.
The traffic collision avoidance system creates a digital bubble, coordinating with nearby planes to prevent mid-air impacts.
As the descent begins, the aircraft transforms, extending landing gear and spoilers to shed speed and altitude.
On the runway, carbon ceramic brakes and engine thrust reversers convert massive kinetic energy into heat and noise. Every second of data is captured by flight recorders, ensuring that every lesson learned improves future safety. Aviation is the pursuit of perfection, where technology and human skill conquer the sky every single day. Aviation faces its biggest challenge yet, reducing its carbon footprint in an era of global connectivity.
Sustainable aviation fuel, derived from renewable sources, can drop into existing engines without mechanical modification.
Engineers are also exploring electric propulsion for short-haul flights, replacing heavy turbines with silent, zero-emission motors.
Hydrogen-powered concepts use fuel cells to create electricity, with the only byproduct being pure water vapor.
New wing designs, inspired by the soaring wings of albatrosses, promise to further slash drag and fuel consumption.
The goal is net zero, a future where we explore the planet without leaving a trace behind.
Every innovation brings us closer to a world where the sky is as clean as it is vast.
The journey toward a sustainable horizon has only just begun. Join us as we build the future.
If you enjoyed this deep dive into the physics of flight, don't forget to like and subscribe. Check out our other videos to explore more wonders of engineering. Until next time, keep looking up.